Okay, chapter 12, we're looking at the properties of water. Firstly, what is latent heat? Latent heat is the energy absorbed by a fixed amount of substance as it changes state from a solid to a liquid or from a liquid to a gas. And then we get latent heat of fusion and latent heat of vaporization. So for latent heat of vaporization, you need to think of a vapor. So obviously a liquid is going to a gas. So latent heat of vaporization is the heat energy needed to change 1 mole of a substance from a liquid to a gas at its boiling point. Okay, you need to remember that at its boiling point, that's when a liquid will change to a gas. Okay, the next point, the latent heat of fusion of a substance is the heat energy required to change 1 mole of substance from a solid to a liquid at its melting point. So a phase change from a solid to a liquid occurs at its melting point, right? And that's related to the latent heat of fusion. Also, the latent heat of fusion, the units for latent heat is kilojoules per mole. Now with specific heat capacity is the amount of energy in joules that are needed to increase the temperature of a certain amount, which is usually 1 gram of water by 1 degree Celsius. So basically your unit for specific heat capacity is joules per gram per degree Celsius. So joules is basically the amount of energy you need to supply per 1 gram of substance to increase the temperature 1 degree Celsius. So for example, for water, the specific heat capacity is approximately 4.2 kilojoules per gram per degree Celsius. The specific heat capacity for water is about 4.2 joules per gram per degree Celsius, not kilojoules. The other thing, for example, if you look at ethanol, the specific heat capacity is 2.4 joules per gram per degree Celsius, and aluminium, for example, is 0.90 joules per gram per degree Celsius. Right, now looking at the last point, what if ice was more dense than water? This is a question I want you to think about. Maybe do some research or look at the relevant textbook for why do you think ice is more dense or what if ice was more dense in water? What impact would it have to the fish or the plants in river systems or in water systems, etc.? I'll leave that for you to do as an exercise. Okay, now we look at water as a universal solvent. This is chapter 13 from the prescribed text, the new textbook. So you can hit the pause button and just have a look at the points made, the 1, 2, 3, 4 dot points, and we'll get back to this. What the rule of like dissolves like? It's a rule used to predict that polar solutes will dissolve in polar solvents and non-polar solutes will dissolve in non-polar solvents. A common example of a polar molecular substance, a polar solvent, would be water. Water will dissolve polar molecular compounds like ethanol, for example. And ethanol will form hydrogen bonds with water. Right. On the other hand, you can have polar molecules. For example, if you look at hydrochloric acid or hydrogen chloride, HCl, because there's such a strong polarity in the bond that when added to water it would immediately ionize to form hydrated ions. And now I want you to think about the bond ethanol forms with water when it dissolves in water. I've just discussed that. And also what is the purpose of this type of bonding? How does it help? And also consider hexane as a non-polar molecule. Think of substances that will dissolve in hexane or ethane, for example, which are both non-polar. Okay, in addition to the polar molecules already discussed, like HCl, for example, you get other ionic compounds like sodium chloride, NaCl, which will dissociate in water to form hydrated ions. I've given an example of a precipitation reaction showing sodium chloride reacting with silver nitrate, giving us silver chloride, which is the solid, that's the precipitate, and sodium nitrate, which is aqueous. So if a question asks you for writing a balanced equation including the states, that's how it is written. And to know whether a precipitate is going to form, you must know solubility rules. So solubility rules is very important. I suggest you go back to your textbooks, look at the appendix, or know the Snape rule as discussed in the new textbook on what product's going to be soluble in water, what's going to form a precipitate. Another set of equations and a writing of equations that's worth describing at this point is how do you write full equations for precipitation reactions and how do you write ionic equations. Let's consider the example of aluminium nitrate plus sodium sulfide, giving us aluminium sulfide plus sodium nitrate. I've written the full equation. You can see that it is balanced, and you need to be able to produce an equation like this and be able to balance an equation. So I suggest you practice this. Now for an ionic equation, you have to remove the spectator ion. So you need to go and look at your textbook on what spectator ion is, and it doesn't take part in the ionic equation. Now another quick way that textbooks discuss is to start with the precipitate. So on the right hand side we have Al2S3, which is aluminium sulfide, which is the precipitate. Okay, so we write that first, as you can see written in purple there. Then next you add the formula of ions that forms the precipitate. Now to form the Al2S3, what I need will be aluminium 3 plus and S2 minus. But I need 2 moles of aluminium 3 plus and 3 moles of S2 minus to give us that. Then you just confirm that the equation is balanced, and in this case, yes, it is. Okay, now we move on to chapter 14 in the new textbook. We're looking at solubility curves, crystallizations, dilutions, and concentrations. Okay, firstly, the important question which you really need to know what saturated, supersaturated, and unsaturated means. Now looking at saturated first, we need to know that a saturated solution is one in which no more solute can be dissolved at a particular temperature. Then an unsaturated solution contains less solute than is needed to make the solution saturated. So what this means is that an unsaturated solution can dissolve more solute. Okay, and a supersaturated solution is an unstable solution that contains more dissolved solute than a saturated solution. Right, so if this type of solution is disturbed, some of the solute will separate from the solvent as a solid. Okay, I will try and explain more of saturated, unsaturated, and supersaturated when we look at when we look at an example below. Okay, the example below is a question we covered in class. It's from the prescribed textbook. Okay, I've got the worked out answers next to it as well. The question is asking us what mass of potassium nitrate will dissolve in 500 grams of water at 70 degrees Celsius. See, we go to the solubility curve. We see at 70 degrees, that's where I've drawn the red line, go up vertically and go across horizontally, we see that at 70 degrees Celsius, 140 grams of potassium nitrate dissolves in 100 grams of water. So I want to know how many grams dissolve in 500 grams of water. I multiply my denominator and numerator by 5 to get 500 grams of water in the denominator. So that tells me there will be 700 grams of potassium nitrate in 500 grams of water at 70 degrees Celsius. The next question, if 25 grams of potassium nitrate was added to 50 grams of water at 70 degrees, how much must be added to make a saturated solution? So 25 grams per 50 grams. Remember, the solubility chart given or solubility curve given is per 100 grams water. Because I got 50 grams water, I need to make it to 100 grams of water, so I'll multiply the denominator by 2. I have to multiply the numerator by 2. So I got 50 grams of potassium nitrate over 100 grams of water. So the solubility at 70 degrees is 140 grams over in 100 grams of water. So to make the solution saturated, I need to add 140 minus 50, another 90 grams of potassium nitrate. So now this means if I add more than 90 grams of potassium nitrate, I'm going to have a supersaturated solution. So that means I've got more solute, which is the potassium nitrate, that can actually dissolve in the solvent. Okay, hope you follow that.